This video will introduce some fundamental concepts associated with Fourier transform or frequency domain analysis. It will also introduce a few different applications where frequency domain analysis is extremely useful. Most of you are familiar with the idea of frequency. Basically, it is the rate at which something wiggles. Manifestations of frequency in the physical world are everywhere. For example, the pitch of a sound is determined by its frequency. For electromagnetic radiation, frequency determines what kind of radiation it is, ranging from infrared light at low frequencies to X-rays and gamma rays at high frequencies. For visible light, frequency determines its color. Frequency also determines the energy associated with photons. X-rays and gamma rays have higher energy photons than light in the visible spectrum. So there are many ways in which frequency shows up in the natural world. Frequency also shows up in science and engineering in ways that are not due to the natural world, but are rather a mathematical tool. We often use a frequency domain analysis to solve mathematical problems, which may be modeling physical phenomena. This picture shows computed values of the temperature for a heat sink. On this edge, you've got a hot CPU or other component generating heat, and out here you have temperatures. The distribution of heat within the heat sink obeys the heat equation. The heat equation, which is a partial differential equation, can be solved using frequency domain analysis. There is no intrinsic frequency associated with the heat, but the mathematical techniques of the frequency domain analysis make it possible to analytically solve these sorts of problems. Now, in the spirit of complete disclosure, the heat distribution you see here was actually computed using finite element analysis on a computer. Partial differential equations that model real-world objects are almost always solved on a computer now, because you can look at much more complex scenarios than you can if you're solving analytically. Fourier analysis has also been used to investigate vibrating strings, solving for modes and frequencies. It's been used to investigate the determination of orbits of planets and other celestial bodies, and many other problems. In engineering, we use the concept of frequency in many different ways. One way in which we use frequency is when we think about a communication system. I have here a cell phone which communicates via radio waves, which are electromagnetic radiation, to a base station, which is basically this tower. If there are several cell phones close to the tower, one of the issues that you face is that if both cell phones are using the same frequency, unless you do things in a very clever way, these frequencies collide with each other and you don't get good information at the base station. On the other hand, if each cell phone transmits in a different frequency, then the base station can sort out which transmissions are coming from which cell phone by looking at the frequencies that they transmit. And that's actually the way that AM radio, FM radio, the ancient analog television, and many other communication systems work. Now again, in the spirit of complete and full disclosure, it turns out that in most cell phone systems, you will have two or more cell phones transmitting on the same frequency. They use other techniques such as time division multiplexing or code division multiplexing to separate the information from the two cell phones. This idea that I can use different frequencies to transmit different stuff has been used since basically we started using radio or developing radio a century ago. Different frequency bands in the electromagnetic spectrum are allocated for each of many different purposes in almost every country of the world. Looking at things in the frequency domain allows you to design communication systems. Another reason to do frequency domain analysis is illustrated by this cryptic set of pictures. Let me try to explain. The idea is that if I have a periodic signal like this badly drawn square wave, basically a function of time, I can represent it in terms of sines and cosines, each with particular frequencies. That's what these diagrams are illustrating. I have a square wave, and in the top picture it shows that I can approximate the square wave with the sine wave. You can see that the sine wave goes up where the square wave goes up, and down where the square wave goes down. By adding another sine wave to my first sine wave, the second sine wave in this particular case has a frequency 3 times the frequency of the first sine wave, I get something that looks like this, which is closer to my square wave. And by adding yet another sine wave that has a frequency of 5 times my fundamental frequency, or the frequency of the first sine wave, you can see that I can get even closer to something that looks like a square wave. The idea is that I can take the square wave and break it down into a sum of sine waves. This is extremely useful. For example, this is quite similar to the process that your ear uses to process noise and sound, to recognize speech, understand your surroundings, and so on, and generally help you make sense of the world. These higher order harmonics, the sine wave that is 3 times the fundamental frequency, 5 times the fundamental frequency, and 7 times the fundamental frequency, these are called harmonics. Harmonics in part create the different sound characteristics that make a flute sound much different than a trumpet. At a basic level, harmonics determine what musical instruments sound like. Speech recognition and speech compression use the idea that I can break signals into different frequencies. For example, in speech compression, you might take a signal and convert it into a frequency domain representation which might look something like this. The horizontal axis is frequency, and the vertical axis shows the power at each frequency in the signal. You might compress this signal by representing its frequency spectrum by a bunch of straight line segments. You can transmit the parameters of the line segments over a communication channel using far fewer bits than you can transmit the whole frequency spectrum or the original time signal. So, for the last idea in this video, compressed audio, like MP3 files, as well as video and speech recognition, and most of the stuff that we associate with the modern digital media, all require a computer. Fourier analysis allows us to convert between continuous time signals. Continuous time signals are the sort that you pick up with a microphone, and discrete time signals. Say, for example, I have some arbitrary signal that looks like this. It might be speech or music or some other signal that I'm interested in. By using Fourier analysis, I can determine how many samples of the signal I need to represent it accurately in a computer. A sample is basically looking at the signal at a particular point in time and taking its value and quantizing that. Fourier analysis lets you compute how many samples of the signal you'll need in order to be able to reconstruct the signal at a given degree of accuracy. This is extremely important because in order to process a signal in a computer, you have to have samples. Computers don't operate on continuous time signals. You need to take samples and then convert them into bits. So, this concludes this brief introduction to frequency domain analysis and some example applications in which it's used. I hope you found it helpful.